Hello there, and welcome to the Serene Scroll. I am so glad you are here. Perhaps it has been a long day, filled with the noise and hurry of the world. Now is the time to let all of that gently fall away. Here in this quiet space, we will journey together, not through the world of our daily lives, but into the vast, silent story of existence itself. So find a comfortable position, allow your body to feel heavy and supported, and let your breath slow. And just before we begin our journey into the cosmos, if these quiet explorations help you unwind or give you a peaceful way to end your day, consider gently tapping the like button and subscribing to the channel. There is no need to do anything now. Simply allow the thought to drift by like a cloud in the night sky. And now, let us begin. Imagine, if you will, that the entire history of the universe is a single immense book. It is bound in darkness, and its pages are sprinkled with light. This book contains everything, every star ever born, every world that has ever turned, every thought that has ever been thought. But we as readers have a peculiar challenge. We have opened this great book not to its first page, but to its very last. We are living in the final sentence of the final chapter, written in the present moment. And so, the question that has haunted humanity for millennia, where did all of this come from, requires us to do something remarkable. It requires us to learn how to read this cosmic story backward. Our detective story begins in the simplest of places, a clear night. You stand beneath the deep velvet canopy of the sky, far from the glow of city lights. The air is cool on your skin. A profound silence surrounds you, broken only by the gentle sound of your own breathing. Above 1 billion pinpricks of light are scattered across the darkness. They seem immediate, as if they are all there with you in this very moment. But this is the first and most beautiful illusion the universe presents to us. The night sky is not a static painting. It is a time machine. Every point of light you see, every star, every distant hazy galaxy is an echo. The light from these celestial bodies has traveled for an immense amount of time to reach your eyes. It is a messenger from the past. Light, while incredibly fast, does not travel instantaneously. It moves at a finite and constant speed, about 300,000 kilometers every second. This seems impossibly quick, but space is impossibly vast. The light from our own moon, our closest celestial companion, takes a little over 1 second to reach us. When you look at the moon, you are seeing it as it was 1 second ago. The light from our sun, the heart of our solar system, takes over 8 minutes to make its journey. Every time we feel its warmth, we are feeling the warmth of the sun as it was 8 minutes in the past. This concept, known as look-back time, is the first key we need to decipher the cosmic book. As we look further out into space, we are looking deeper into time. The nearest star to our own Proxima Centauri is over 4 light-years away. The faint light we see from it tonight began its journey 4 years ago, when the world was a different place. The beautiful bright star Vega, a jewel of the summer sky, is 25 light-years away. The photons striking your retina from Vega tonight started their voyage a 1/4 of a century ago. Many of the stars that form our familiar constellations are hundreds, even thousands of light-years away. Their light is a postcard sent from a time when empires rose and fell here on Earth. And when we look beyond the stars of our own galaxy, the Milky Way, our journey back in time becomes truly staggering. That faint, fuzzy patch of light, visible in the autumn sky, the Andromeda Galaxy, is our closest large galactic neighbor. It is 2.5 million light-years away. The light you see from it is a relic from a time long before modern humans walked the earth. It is a ghost of light, an ancient message telling us what Andromeda looked like 2.5 million years ago. We are seeing its past preserved in the steady stream of photons crossing the cosmic void. For centuries, this was simply a profound philosophical idea. But in the early 20th century, it became the foundation for a revolution in our understanding. This is where our story's first great detective enters the scene, an astronomer named Edwin Hubble. Imagine him in the 1920s, high atop Mount Wilson in California, in the cold, thin air of the night. He is inside the dome of the 100-inch Hooker telescope, at that time the most powerful in the world. It is a place of deep quiet and focused attention. The giant machine moves with a soft mechanical hum, a modern marvel aimed at the ancient sky. Hubble was not just a stargazer. He was a meticulous cartographer of the cosmos. His goal was to settle a great debate of his day: were the faint spiral smudges of light, then called nebulae, small clouds of gas within our own Milky Way, or were they, as some suspected, entire island universes, galaxies, just like our own, but incomprehensibly far away? Using the telescope's immense power, he was able to spot individual stars within the Andromeda Nebula. By studying a special type of star that pulses at a predictable rate, he could calculate its true brightness. And by comparing its true brightness to how dim it appeared from Earth, he could calculate its distance. The answer was astonishing. Andromeda was not a nearby cloud. It was nearly 1 million light-years away at the time of his first calculations, and later revised to be even further. The universe was not just our galaxy. It was a vast sea of countless galaxies, each one a collection of billions of stars. Humanity's known universe expanded in an instant from one galaxy to a multitude. But this was only his first discovery. It was the second that truly began to unwind the story of creation. As Hubble and his colleagues observed these distant galaxies, they analyzed their light. They noticed something strange, something consistent across almost every galaxy they looked at. The light was stretched, just as the sound of a siren changes pitch as it moves towards you and then away from you. The light from a galaxy changes color depending on its motion. Light from an object moving towards us is compressed, shifting towards the blue end of the spectrum. Light from an object moving away from us is stretched, shifting towards the red end. This is known as redshift. And what Hubble found was that almost every galaxy in every direction he looked was redshifted. They were all moving away from us. This was a profound and unsettling discovery. But the most remarkable part was the pattern he uncovered. The farther away a galaxy was, the greater its redshift. The farther away it was, the faster it was flying away from us. This was the ultimate clue. This was the cosmic book's plot revealing itself. The universe was not a static, eternal stage on which the stars played out their dramas. The universe itself was in motion. It was expanding. To understand this, let's use a gentle image. Imagine a loaf of raisin bread dough before it is baked. You are sitting on one of the raisins. As the dough rises and expands, you look around you. From your perspective, every other raisin is moving away from you. The raisins closest to you are moving away slowly. The raisins on the far side of the loaf are moving away much more quickly. Every raisin is moving away from every other raisin. No single reason is the center of the expansion. The expansion is happening everywhere in the very fabric of the dough itself. This is what Hubble had discovered about the universe. It is not that galaxies are flying through a pre-existing empty space. Rather, the fabric of space-time itself is stretching, carrying the galaxies along with it. This is why it appears that everything is moving away from us. An observer in any other galaxy would see the exact same thing, all other galaxies moving away from them. This discovery turned cosmology on its head. For if the universe is expanding now, then it logically follows that in the past it must have been smaller. If we could run the film of the cosmos backward, we would see all the galaxies rushing back towards each other. The space between them would shrink. The universe would become denser. It would become hotter. If you go back far enough, everything we see, all the hundreds of billions of galaxies each, with their hundreds of billions of stars, would have been compressed into a space smaller than a single atom. This was the first direct observational evidence that the universe had a beginning. It wasn't an eternal, unchanging void. It had a history. It had a starting point. Our detective story had found its first chapter. But for this story to be coherent, for us to apply our findings here to the universe as a whole, we must rely on one more foundational idea. It's a principle of humility, really. It's called the cosmological principle. It is a simple but powerful assumption that on the very largest scales, the universe is much the same everywhere. It states that the universe is both homogeneous and isotropic. Homogeneous simply means that there are no special places. No matter where you are in the cosmos, the general view, the density of galaxies, the types of structures you see will be roughly the same. Of course, on small scales, this isn't true. A star is very different from the empty space next to it. A galaxy is very different from the void between galaxies. But if you zoom out far enough so that entire clusters of galaxies are just tiny specks, the universe smooths out into a uniform tapestry. There is no grand cosmic palace at one end and a barren desert at the other. It is all more or less the same material. Isotropic means that there are no special directions. From our vantage point, the universe looks the same no matter which way we turn our telescopes. We don't see all the galaxies clumped in one part of the sky and a great emptiness in the other. They are distributed evenly in a great shimmering web across the entire celestial sphere. This principle is what allows us to be cosmic detectives. It tells us that what we observe from our small blue planet is not some local anomaly. It is representative of the universe as a whole. The laws of physics that we uncover here, the behavior of light, the force of gravity, are the same laws that govern the most distant galaxies we can see. It means the story we are deciphering is not just the story of our neighborhood. It is the story. It gives us the confidence to take our clues, the redshift of distant galaxies, the finite speed of light, and to extrapolate them backward, deep into the mists of time. So we have our method. We use the sky as a time machine, knowing that the further we look, the earlier the chapter we are reading. We have our central plot point, a universe that is expanding its story, one of constant unfolding change. And we have our guiding principle, the assumption that the story is coherent and the same for all readers, no matter where in the great cosmic library they may be. We are standing on the last page looking back. We have learned to read the language of stretched starlight, which tells a tale of everything moving away from everything else. This points us inexorably backward to a time of immense density and heat, a time before stars, before galaxies, before even the atoms that make up your body. It points to a singular moment of origin, but reading the light from the first galaxies can only take us back so far. There is a limit. We can look back 13 billion years or more to see the faint smudges of the very first star systems forming. But what came before that, before the first star ignited the universe, was a dark, hot, dense fog. There was no starlight to be seen because there were no stars to produce it. How then can we ever hope to find a clue from that even earlier time? How can we read a page from the book that was written before light itself was set free? If the universe truly began in a hot, dense state, there must be some relic left over from that primordial fire. Not a light from a single star, but a glow from the universe itself. A faint, ancient warmth that should still permeate all of space. A whisper from the moment of creation, still echoing through the cosmos today. Our cosmic detective story required another clue, something far more subtle than the light of galaxies. It required us to learn how to listen for the faintest whisper of the beginning. And just before we begin our journey into the heart of the great beginning, let us first listen, not with our ears, but with a deeper sense of attention. Let us listen to the silence. Imagine yourself floating in the deep velvet blackness between the stars. It is a quiet, unlike any on Earth. There is no wind rustling through leaves, no distant hum of traffic, no gentle sound of your own breathing in the vacuum. It is a profound, absolute stillness. For centuries, this is what we believed space to be, the great, silent emptiness. We looked out with our eyes, with our telescopes, and saw islands of light galaxies, stars, nebulae, separated by an ocean of perfect, silent dark. But what if that silence wasn't empty? What if the entire cosmos was humming with a message, a faint and ancient whisper from its own birth? A sound so old and so universal that it was everywhere at once, and therefore nowhere at all mistaken for the simple noise of our own instruments. This is the story of how we learned to hear that whisper. It is the story of finding the first echo of creation. Our story begins not in a grand observatory on a remote mountain peak, but in a more humble setting, Holmdel, New Jersey, in the year 1964. Two young radio astronomers, Arno Penzias and Robert Wilson, were working with a magnificent piece of equipment. It was a large horn antenna, shaped like a colossal ear trumpet aimed at the sky. It was built not to search for the origins of the universe, but for a far more practical purpose, to detect faint radio signals bouncing off early communications satellites. To do their job properly, they needed to eliminate every possible source of background noise. They were hunting for a perfect, clean silence, a pure channel through which a satellite's faint signal could pass, but they couldn't find it. No matter where they pointed their giant antenna, no matter the time of day or the season of the year, there was a persistent, low, steady hiss. A faint microwave hum that came from every direction in the sky with equal intensity. At first, they thought it was the equipment itself. They checked every switch, every wire, every connection. They rebuilt parts of their receiver. The hiss remained. They considered radio interference from nearby New York City, but the signal was the same even when the antenna was pointed away from the urban sprawl. The hiss was isotropic, the same in all directions. They began to grow frustrated. Their meticulous work was being contaminated by this stubborn, unwanted noise. They even entertained a rather terrestrial explanation. A pair of pigeons had taken to roosting inside the warm, sheltered horn. Perhaps they reasoned the birds' droppings what they politely called a white dielectric material were producing some kind of thermal noise. And so, in one of the more curious episodes in the history of science, the two future Nobel laureates climbed into their giant cosmic microphone and scrubbed it clean. The pigeons were permanently relocated, and still the hiss remained. It was a cosmic mystery hiding in plain sight. This faint uniform hum wasn't coming from Earth, or from the Sun, or even from our own Milky Way galaxy. If it were from our galaxy, it would be louder in the direction of the galactic center and fainter in others. But it was perfectly smooth, perfectly constant wherever they looked. It was as if the very fabric of space itself was glowing faintly at a temperature just a few degrees above absolute zero. What Penzias and Wilson had stumbled upon entirely by accident was not noise. It was the oldest light in the universe. It was the faint, cooling ember of the Big Bang itself. To understand what this light is, we must travel back in time with our imagination. Back beyond the first stars, beyond the first galaxies, to a time when the universe was less than 400,000 years old. In this infant state, the cosmos was not the dark, transparent space we know today. It was a completely different realm. It was a seething, hot, opaque fog. The entire universe was hotter than the surface of a star, a blistering, glowing plasma of fundamental particles, protons, neutrons, electrons, all churning in a brilliant bath of light. In this primordial soup, light could not travel freely. A photon of light would be emitted, but it would immediately slam into a free roaming electron, be absorbed, and sent careening off in a new direction. The universe was like a dense, impenetrable fog, where you cannot see your hand in front of your face, because the light is scattered in all directions. The cosmos was full of light, but it was trapped, locked in a frantic dance with matter. But the universe as we know was expanding, and as it expanded, it cooled. For hundreds of thousands of years, this cooling process continued slowly, inexorably. Then it reached a critical threshold, a magic temperature of about 3,000 degrees Kelvin. At this point, the universe was cool enough for the frantic dance to end. The free electrons which had been scattering the light were now slow enough to be captured by the protons and neutrons, forming the first stable neutral atoms, mostly hydrogen and helium. This moment is called the epoch of recombination. And in that moment, the universe underwent a breathtaking transformation. Suddenly the fog cleared. The photons of light, which had been trapped in the cosmic plasma for millennia, were now free. With the electrons now bound up in atoms, the universe became transparent for the very first time. The light was liberated, set free to travel in straight lines across the cosmos unimpeded. The faint hiss that Penzias and Wilson discovered was that very light. It is the first light ever to travel freely through space. For 13.8 billion years, it has been journeying across the expanding universe. And as the universe has stretched, so too has this light. Its wavelength has been stretched from the brilliant visible light of a hot plasma into the long, cool, invisible wavelengths of microwaves. It is a fossil, an echo, the afterglow of a creation event that filled all of space. We call it the cosmic microwave background, or the CMB. When we look at this light with our modern satellite telescopes, we are not looking out into space so much as we are looking back in time. We are seeing the universe as it was at the moment it became transparent. We are looking at the surface of that primordial fireball. The CMB is quite literally the oldest photograph we will ever possess. It is the universe's baby picture. And like any baby picture, it holds profound clues about what it would grow up to become. When our satellites like COBE WMAP and Planck mapped this ancient light in detail, they confirmed what Penzias and Wilson had first found. It is astonishingly uniform. The temperature of this background radiation is the same to 1 part in 10,000 no matter which direction we look. This uniformity is a powerful confirmation of the Big Bang Theory. It tells us that the entire universe did indeed emerge from the same hot, dense state. If it hadn't, there would be no reason for distant regions of the sky, which have never been in contact, to share the exact same temperature. But here, the story takes an even more beautiful turn. For when we look at this ancient photograph with incredible precision, we find that it is not perfectly uniform after all. There are tiny, minuscule fluctuations in the temperature, minuscule imperfections. Some spots are ever so slightly warmer, 100,000th of a degree warmer, and some are ever so slightly cooler. On the maps, we create these fluctuations appear as a modeled pattern of faint blue and red patches against a uniform background. And at first, they might look like simple noise or static, but they are the most important features in the entire cosmos. These tiny temperature variations are the seeds of everything that exists today. The slightly warmer, redder spots on the map correspond to regions in the early universe that were infinitesimally denser than average. The slightly cooler, bluer spots were infinitesimally less dense. It is a map of the universe when it was almost perfectly smooth, but not quite. And in cosmology, almost perfect is everything. Imagine a vast still lake, its surface as smooth as glass. And then imagine the faintest, most subtle ripples on its surface almost too small to see. Those ripples are like the fluctuations in the cosmic microwave background. They are the imprint of primordial tremors, quantum fluctuations from the very first moments of time, magnified by cosmic expansion to an astronomical scale. Over the vast expanse of cosmic time, gravity went to work on these tiny seeds. The slightly denser regions, those warmer patches, had a slightly stronger gravitational pull. Over millions of years, they began to gently tug in more matter from their surroundings. They became the gravitational anchors, the gathering points around which the first wisps of gas began to collect. The process was achingly slow, playing out over hundreds of millions of years in the dark, infant universe. Slowly, these denser regions grew, pulling in more and more hydrogen and helium gas. They became vast clouds which collapsed under their own weight, their cores growing hotter and denser still, until they ignited in the fires of nuclear fusion. These were the first stars. These stars gathered together, drawn by their mutual gravity, to form the first galaxies. And those galaxies in turn were pulled together along the invisible lines of force laid out by those primordial fluctuations, forming the great clusters and superclusters of galaxies we see today. The vast web-like cosmic structure of the modern universe, the filaments of galaxies stretching across millions of light years separated by immense empty voids, is a direct descendant of those tiny humble spots on the CMB map. Every star, every planet, every galaxy, indeed, you and I, we are all in a very real sense the result of those minuscule imperfections in the fabric of the early universe. We exist because the beginning was not perfectly smooth. The faint whisper that Penzias and Wilson found was not just the echo of the universe's birth, but the blueprint for its entire future. It is a humble, quiet testament to how the largest structures we can imagine grew from the smallest seeds imaginable. This ancient light gives us a photograph of the universe when it was a newborn, a cosmos composed of simple atoms just beginning to emerge from the light. It shows us a universe of hydrogen and helium, the fundamental building blocks glowing on the precipice of a long and dark age before the first stars would shine. But this picture raises an even deeper question. This light was freed when the first atoms formed. But how were the very nuclei of those atoms, the protons and neutrons, that make up all the matter we know, first forged? To answer that, we must journey even further back in time, past the moment this photograph was taken into the inferno that preceded it. We must leave the age of light and enter an age of pure, unimaginable fire, to the time when the universe was not years, but mere minutes old. And just before we begin our journey into the heart of the great beginning, let us first listen, not with our ears, but with a deeper sense of attention. Let us listen to the silence. Imagine yourself floating in the deep velvet blackness between the stars. It is a quiet, unlike any on Earth. There is no wind rustling through leaves, no distant hum of traffic, no gentle sound of your own breathing in the vacuum. It is a profound, absolute stillness. For centuries, this is what we believed space to be: an eternal, silent, and empty stage. But that cold, expansive silence is the descendant of an entirely different state of being. It is the echo of a time that was neither silent, nor cold, nor empty. To understand our universe, we must leave this quiet void behind and travel back. Back before the first star ignited, before the first galaxy spiraled into existence, to a moment of unimaginable energy. We journey to a time when the entire cosmos was smaller than a single grain of sand, yet contained everything that would ever be. Let us travel back to the first 3 minutes. At the very first second of its existence, the universe was not dark. It was a blaze of pure incandescent light, a furnace of such staggering heat that our concepts of temperature lose all meaning. Billions upon billions of degrees. In this primordial state, matter, as we know it, could not exist. There were no atoms, no protons, no neutrons. There was only a seething, turbulent soup of the most fundamental particles imaginable. This was the era of the quark-gluon plasma. Imagine this cosmic broth. Quarks, the tiny constituents that would one day build the hearts of atoms, darted about as free particles unbound. Gluons, the aptly named carriers of the strong nuclear force, flowed between them, knitting the fabric of this energetic sea together. Swirling in this maelstrom were electrons, positrons, and ghostly neutrinos, all locked in a frantic dance with an ocean of photons, particles of pure light. The density was immense, crushing all of space into a single unified energetic point. There was no structure, no order, only a perfect chaotic equilibrium. Everything was in constant collision, annihilating and re-emerging from pure energy in a cycle so rapid it defies imagination. The universe was humming with a vibration so intense it was the sound of creation itself. But the one constant in this new universe was change. The same impetus that sparked its existence was now causing it to expand, and as it expanded, it began to cool. The change was subtle at first, a gradual lowering of the cosmic temperature, but it was enough. As the universe aged from 1 second to 2, the temperature dropped just enough for a monumental transformation to occur. The cosmic recipe was entering its next crucial step. The frenetic energy of the quark-gluon plasma began to subside. The strong nuclear force, once just one part of the chaotic dance, started to assert its nature. It began to pull the free-roaming quarks together, binding them into stable trios. For the very first time, familiar particles began to emerge from the haze. A combination of two up quarks and one down quark formed a proton, a particle with a positive charge, the future nucleus of a hydrogen atom. A combination of one up quark and two down quarks formed a neutron, a particle with no charge. In an instant, the cosmic soup was transformed. It was now a thick gruel of newly minted protons and neutrons, still swimming in a sea of electrons and light. The universe had taken its first step toward structure. It had forged the fundamental building blocks of every star, every planet, and every living thing. Yet these new particles were not entirely equal. The neutron was ever so slightly heavier than the proton. This tiny difference in mass meant that the neutron was less stable. Left to its own devices, a free neutron will naturally decay into a proton in a matter of minutes. In the heat of the early universe, this process was in a delicate balance. Protons could capture electrons and become neutrons, while neutrons could decay back into protons. For a short while, their populations were kept in a near-perfect equilibrium, a constant flux of one turning into the other. But as the universe continued its relentless expansion and cooling, the energy required to turn a proton into a heavier neutron became harder to come by. The scales began to tip. The decay of neutrons into protons started to win out. Slowly, protons began to outnumber neutrons. The ratio shifted, settling at approximately 7 protons for every 1 neutron. This number, this simple ratio, born from a tiny imbalance in mass, would dictate the chemical composition of the entire universe for all of time. The grand cosmic recipe was being followed with uncanny precision. Now, with the ingredients assembled, the next stage was set: the forging of the first atomic nuclei. You might imagine that with protons and neutrons now available, they would immediately begin sticking together. But the universe was still a place of overwhelming violence. It was too hot. For the next minute or so, the cosmos was caught in a frustrating bottleneck. A proton and a neutron could indeed find each other in the dense plasma. The strong force could pull them together to form a nucleus of deuterium, also known as heavy hydrogen. This was the first essential step in building more complex elements. But no sooner would this fragile bond form than it would be shattered. A high-energy photon, a particle of light from the still raging furnace, would slam into the new nucleus and blast it apart, returning it to a lone proton and a lone neutron. Imagine a cosmic dance where partners meet for a fleeting moment, only to be thrown apart by an impossibly energetic crowd. Creation and destruction in a near instantaneous cycle. The universe was trying to build, but its own heat was its worst enemy. For this crucial period, it was as if all of creation was holding its breath. The building blocks were present, the forces were ready, but the conditions were not yet right. No helium, no lithium, nothing more complex than a single proton could survive for long. The cosmic kitchen was too hot, and the delicate structures were burning before they could even set. And then, as the universe approached its third minute of life, the magic moment arrived. The temperature dropped to a critical threshold, about 1 billion degrees. To us, this sounds impossibly hot, but for the early universe, it was the perfect level of gentle warmth. It was finally cool enough. The photons that filled space no longer had enough energy on average to break apart a deuterium nucleus. The bottleneck was broken. What happened next was a chain reaction of creation on a cosmic scale, a glorious synchronized event that unfolded across the entirety of space in just a few minutes. The symphony, after a long and tense crescendo, finally resolved into its first beautiful chord. With deuterium now able to survive, the path was clear. A deuterium nucleus would quickly find another proton or neutron fusing to create more stable arrangements. Two deuterium nuclei could merge to form a nucleus of helium-3. A helium-3 nucleus could then fuse with a neutron to create the ultimate prize, helium-4. Helium-4, with its 2 protons and 2 neutrons, is an extraordinarily stable and tightly bound nucleus. It is a perfect symmetrical structure. Once formed, it was impervious to the remaining heat of the universe. In this brief golden window of opportunity, the universe began furiously converting its raw materials into helium. It was an astonishingly efficient process. The cosmos, in a matter of minutes, cooked almost all of its available neutrons into stable helium nuclei. The 7-to-1 ratio of protons to neutrons now paid off. For every 2 neutrons, there were 14 protons. The 2 neutrons would combine with 2 of the protons to form 1 helium-4 nucleus. That left 12 protons, all by their lonesome. And what is a single proton? It is the nucleus of a hydrogen atom. So when the flurry of creation was over, the result was a universe composed of roughly 12 hydrogen nuclei for every 1 helium nucleus. By mass, this meant the cosmos was now approximately 75% hydrogen and 25% helium. A tiny trace amount of lithium was also forged in the frenzy, but the process overwhelmingly favored the creation of helium. This entire epic of creation, from the breaking of the deuterium bottleneck to the forging of nearly all the helium that would ever exist, lasted for only a few minutes. By the time the universe was about 20 minutes old, it had expanded and cooled so much that the particles were too far apart and moving too slowly for fusion to continue. The density and temperature of the cosmic furnace had dropped below the critical point. The fires of creation were extinguished. The cosmic kitchen was closed. The first chapter of elemental creation was over. The universe had set its elemental composition, a signature that it carries to this day. When astronomers point their telescopes to the most ancient clouds of gas in the most distant corners of the cosmos, they find that they are made of about 75% hydrogen and 25% helium. It is a profound chemical echo, a fingerprint left behind from those first few minutes. Think of this for a moment. Every time you see a child's birthday balloon filled with helium floating gently toward the ceiling, you are looking at atoms whose hearts were forged in that brief, brilliant burst of creation nearly 14 billion years ago. The hydrogen that combines with oxygen to form the water you drink is the very same hydrogen, those lone protons, that was left over from that primordial recipe. We are made of materials that witnessed the dawn of time. The universe is not something separate from us. Its history is written in our very substance. For those few minutes, the entire universe was a single unified star, burning bright and forging the stuff of future stars, future galaxies, and future life. It was a singular event, unrepeatable and perfect in its execution, governed by laws of physics that worked in harmony to build a stage for all that was to come. And yet, as we stand back in awe of this magnificent, well-understood story of the first 3 minutes, a deeper question emerges. We can narrate with confidence what happened at 1 second, at 3 minutes, at 20 minutes. Our models and observations align with beautiful precision. But what happened before that first second? We have journeyed back to a time of immense heat and density, but we have not yet reached the beginning. Our story starts with a universe already in motion, already expanding, already cooling. What wound the cosmic clock and set it ticking? What came before the furnace? As we try to push our understanding back further to the first microsecond, the first nanosecond, and beyond, our familiar laws of physics begin to fray. We are approaching a wall, a boundary not of space or time, but of knowledge itself. To continue our journey, we must now turn our gaze to the most extreme moment of all, to the very edge of reality, and confront the mystery of the singularity. We must approach the Planck wall. And just before we begin our journey into the heart of the great beginning, let us first listen. Not with our ears, but with a deeper sense of attention. Let us listen to the silence. Imagine yourself floating in the deep velvet blackness between the stars. It is a quiet unlike any on Earth. There is no wind rustling through leaves, no distant hum of traffic, no gentle sound of your own breathing in the vacuum. It is a profound, absolute stillness. For centuries, this is what we believed space to be, an empty stage upon which the cosmic drama unfolded. But as we learn to listen more closely, with instruments of incredible sensitivity, we discovered that this silence was not empty at all. It was filled with a faint, persistent hum. The cosmic microwave background radiation, the echo of creation. This echo has been our guide, the faint trail of breadcrumbs leading us back through time. We have followed it past the formation of galaxies, past the birth of the first stars, back into an era when the entire universe was a glowing, opaque fog of plasma. We have journeyed backward for 13.8 billion years, our vessel of understanding, propelled by mathematics and observation. The cosmic landscape has become simpler, more uniform, hotter and denser with every step back. The familiar structures of our universe have dissolved, melting away into their constituent parts. Now we push further still. We are entering the universe's first second. The journey becomes unimaginably swift. We cross entire epochs in the span of a breath. We pass the point where protons and neutrons first formed, a time of cosmic alchemy. We move beyond it to a state where the universe was a quark gluon plasma, a seething soup of fundamental particles before even the most basic components of matter had fully condensed. The temperature and density are beyond any scale we can comprehend on Earth. And still, we press on, guided by the laws of physics, our reliable map of reality. Our map has been drawn by two great theories. One is Albert Einstein's general relativity, the grand architecture of the very large. It describes gravity not as a force, but as the curvature of space-time itself, a beautiful sweeping geometry that dictates the dance of planets, stars, and galaxies. The other is quantum mechanics, the strange and wondrous rulebook of the very small. It governs the flickering probabilistic world of particles, where energy and matter exist in a constant state of flux, a world of uncertainty and entanglement. For all of modern physics, these two theories have been our north and our south, our east and our west. They have guided us faultlessly through the known cosmos. But now, as we travel to the very edge of time, something begins to happen to our map. The coordinates start to warp. The familiar landmarks of physical law begin to blur. We are approaching a boundary, not a boundary of space, but a boundary of knowledge. We are approaching the Planck wall. Imagine yourself now standing at the precipice of this ultimate frontier. Our journey backward has brought us to just 10 to the power of minus 43 seconds after the Big Bang. This is the Planck time. It is a duration so infinitesimally small that it defies all human intuition. To try and grasp it, imagine the time it takes for a beam of light to cross a single proton, one of the building blocks of an atom. Now divide that time by 100 billion. That is the realm we have entered. It is the shortest possible unit of time that has any physical meaning according to our current theories. Here, at this primordial moment, the entire observable universe, all the billions of galaxies, the trillions of stars, everything we have ever known or will know, was compressed into a space smaller than a single subatomic particle. A space so tiny it is known as the Planck length. This is the fundamental pixel of reality, the smallest possible distance our physics can describe. And at this scale, the universe was a place of perfect, unimaginable unity. In our modern world, we experience four fundamental forces of nature. There is gravity, which holds us to the earth and binds the cosmos together. There is electromagnetism, the force that carries light and electricity and governs all of chemistry. And then deep within the atom, there are two more, the strong nuclear force, the unbreakable glue that holds atomic nuclei together, and the weak nuclear force, which governs radioactive decay. These four forces are the pillars of our reality. They seem distinct, separate, and unchanging. But as we rewound the cosmic clock, we watched them merge. First, at incredibly high energies, the electromagnetic and weak forces unified into a single electro-weak force. Go back further to even higher energies, and this electro-weak force is predicted to merge with the strong nuclear force, creating a hypothetical grand unified force. Here, three of the four pillars have become one, but gravity always remains separate. It is the outlier, the force described by the smooth, continuous curves of general relativity, while the other three are described by the discrete, quantized packets of quantum mechanics. They are two different languages describing the same reality. And for most of cosmic history, this has not been a problem. Gravity rules the large scales, quantum mechanics rules the small. They operate in their own domains like two masters of separate kingdoms. But here at the Planck wall, the kingdoms collide. The universe is both infinitesimally small and unimaginably massive and energetic. It is the one place where both general relativity and quantum mechanics must apply simultaneously. And here, our two great theories, our perfect maps, fail us completely. When we try to use their equations to describe this state, they break. They churn out nonsensical answers, like infinities. The mathematics ceases to describe a physical reality, and instead points only to its own limitations. It is like trying to look at your own reflection in the surface of a pond, but at the exact point where a stone has just been thrown in. The ripples are so violent, so chaotic that no coherent image can form. The light is still there, the water is still there, but the medium is too disturbed to carry meaningful information. So it is with space-time at the Planck scale. Quantum effects would create a roiling, chaotic foam of space-time where distances and durations lose all stable meaning. The smooth fabric of Einstein's universe is torn apart by the violent uncertainties of the quantum world. This is the Planck wall. It is not a physical barrier we have crashed into. It is a conceptual one. It is a shimmering, impenetrable curtain of light woven from the limits of our own understanding. It is the point where our science as we currently know it can go no further. We can stand before it. We can describe its properties from our side, but we cannot see through it. Beyond this wall lies the ultimate question: what was before the Big Bang? Or, perhaps, is the question itself meaningless? At the Planck scale, time itself is no longer the smooth, forward-flowing river we experience. It becomes granular, uncertain. The very concepts of before and after may dissolve into the quantum foam. Asking what came before the Big Bang might be like asking what is north of the North Pole. It's a question that misunderstands the nature of the coordinate system itself. And what of the singularity? We have often been told that the universe began from a single point of infinite density and temperature. An infinitely small, infinitely hot dot. This idea of the singularity is in many ways a product of our theories breaking down. When general relativity is run backward in time, its equations predict that all the matter and energy of the universe converges on a single zero-sized point. But this infinity is precisely the kind of answer that signals a theory has been pushed beyond its realm of applicability. So it is more accurate, and perhaps more beautiful, to think of the singularity not as a physical object, but as a placeholder for our ignorance. It is the X on an ancient mariner's map, marking the edge of the known world with the words, "Here be dragons." It does not mean there are actual dragons there. It means we do not know what is here. Our journey ends and mystery begins. The singularity is not a description of the universe's origin. It is a description of the limit of our description. And in this, there is a profound humility. To stand at the Planck wall is to be confronted with the vastness of what we do not know. It is to recognize that our most powerful tools of thought have a finite range. It is an act of intellectual honesty to say, here, our story must pause. There is no sense of failure in this. On the contrary, there is a deep and quiet sense of awe. We have traveled to the very threshold of existence, to the first countable moment of time. We have followed the logic of the cosmos back to its source, only to find a veil that we cannot yet pierce. And that is a beautiful thing. It means the universe still holds its ultimate secret. It means there are still wonders beyond our current imagination, waiting for a new language, a new idea, a new kind of map to reveal them. Theories like string theory and loop quantum gravity are our first attempts to sketch what might lie on the other side of that curtain, attempts to weave gravity and the quantum world into a single, unified theory of everything. But for now, they remain beautiful speculative mathematics, not yet confirmed by observation. So we stand here in this timeless moment, before time began floating, before this shimmering wall of unknowing. We are not frustrated by the boundary, but are instead filled with a peaceful reverence for the mystery it protects. It is a reminder that the pursuit of knowledge is not just about finding answers, but also about learning to live with the questions. It is about embracing the limits of our perspective and finding wonder in the existence of a frontier. But our journey is not entirely over. While we cannot see through the wall, we can carefully examine what happened in the instant after it. We can look at the state of the universe in its very first breath in the moments that immediately followed this Planck epoch. And when we do, we find another set of profound puzzles. The universe that emerged from this era seems to have been born with some incredibly specific, seemingly fine-tuned properties. It was astonishingly uniform in temperature from one side to the other, even though there hadn't been enough time for heat to travel across it and even things out. It was also geometrically flat, balanced on a knife's edge between expanding forever or collapsing back in on itself. How did the universe emerge from the unknowable chaos of the Planck era with such impossible smoothness and perfect balance? It's as if a colossal explosion, far greater than any we know, had somehow resulted in a perfectly spherical, flawless crystal. This perfection seems to demand an explanation. It suggests that something extraordinary and powerful happened in that first sliver of a second, something that took the raw, unified state of the Planck era and stretched it, smoothed it, and set the stage for the entire cosmic story that would follow. It was an event that would act as the universe's first deep breath, a moment of hyper-expansion that would solve these puzzles and plant the seeds for every galaxy we see today. And just before we begin our journey into the heart of the great beginning, let us first listen, not with our ears, but with a deeper sense of attention. Let us listen to the silence. Imagine yourself floating in the deep velvet blackness between the stars. It is a quiet, unlike any on Earth. There is no wind rustling through leaves, no distant hum of traffic, no gentle sound of your own breathing in the vacuum. It is a profound, absolute stillness. For centuries, this is what we believed space to be, an eternal silent stage upon which the drama of stars and galaxies would unfold. But the story of the universe's origin is not one of silence. It is a story of an event so powerful, so transformative, that its echoes still shape everything we see and everything we are. As we peer back through the cosmic ages, past the galaxies and the first stars, back to the initial moments of creation, our neat and tidy picture of a simple, hot, dense beginning starts to show strange and beautiful inconsistencies. Like a perfectly preserved ancient text, with a few pages that seem to be written in an entirely different language, the standard story of the Big Bang presented cosmologists with puzzles so deep they pointed to a missing chapter, a prologue of unimaginable scale. The first puzzle is one of uncanny uniformity. When we look out at the cosmos in every direction, we see the faint residual heat of creation, the cosmic microwave background. It is the afterglow of the Big Bang, a baby picture of the universe. And this picture is astonishingly smooth. The temperature of this ancient light is virtually the same everywhere, varying by only 1 part in 100,000. To understand why this is a puzzle, imagine 2 distant villages on opposite sides of a vast, impassable mountain range. For all of recorded history, there has been no contact between them. Yet when explorers finally reach both, they find the villagers speak the exact same dialect, share the exact same obscure folktales, and prepare their food with the exact same unique spice. It would be an impossible coincidence. There must have been a time long ago before the mountains rose when they were part of the same community, sharing a common culture. So it is with the universe. When we look at one edge of the observable cosmos, and then at the opposite edge, we are looking at 2 regions that are separated by nearly 28 billion light-years today. Given the age of the universe and the constant speed of light, there has not been enough time for these 2 regions to have ever been in contact, to have ever exchanged heat or information. They should not know about each other. They should not have the same temperature. Yet they do. This is the horizon problem. It's a whisper from the dawn of time that something essential is missing from our story. The second puzzle is one of impossible balance. The geometry of our universe, the very fabric of space-time, appears to be almost perfectly flat. This might sound simple, but it is perhaps the most profound fine-tuning problem in all of science. The overall density of matter and energy in the cosmos determines its shape. If the density were just a tiny fraction higher, gravity would be overwhelming. The universe would have ceased its expansion long ago and collapsed back in on itself in a big crunch. If the density were a tiny fraction lower, the expansion would have been too powerful. Galaxies would never have formed. Stars would never have ignited. The universe would be a cold, diffuse, and empty wasteland. The universe walks a razor's edge. To be as flat as it is today, the initial density of the universe at 1 second old had to be tuned to an accuracy of 15 decimal places. To throw a dart from one end of the known universe and hit a single atom at the other would be a feat of greater probability. It's like finding a pencil that has been balanced on its microscopic tip for over 13 billion years. This is the flatness problem. It suggests that the universe didn't just happen to be this way. It was driven to be this way by some powerful, unseen force. These two great riddles, the impossible uniformity and the impossible balance, called for a new idea. And the idea that emerged was as radical as it was elegant. It was a vision of the universe's first breath, a theory known as cosmic inflation. Let us travel back now to a time so early it almost defies imagination. Not millions or thousands or even a few seconds after the beginning, but to a sliver of a moment so infinitesimally small, it makes a single second seem like an eternity. We are at 1/1,000,000,000 of a trillionth of a trillionth of a second after the Big Bang. Here, in this primordial state, the universe is smaller than a single proton. All the potential for all the galaxies, stars and planets, for every mountain and ocean for you and for me, is contained within a point of unimaginable energy density. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are not yet distinct. They are unified in a single supersymmetrical state. And here, in this moment, something extraordinary happens. A new kind of energy field, a phantom field we now call the inflaton, dominates the cosmos. This field possesses a strange and wonderful property, repulsive gravity. Instead of pulling things together, it pushes everything apart with ferocious, exponential power. This is the trigger. The universe takes its first deep cosmic breath. In the span of that impossibly small fraction of a second, the universe begins to expand. Not at the steady pace we see today, but in a sudden, violent, hyper-accelerated surge. This is inflation. It is a doubling and a redoubling and a redoubling of space itself. In a mere 10 to 32 seconds, the universe increases in size by a factor of at least 10^26. That's a 1 followed by 26 zeros. It is like taking a single grain of sand and in less than the blink of an eye expanding it to the size of our entire observable galaxy. As this divine breath rushes outward, it smooths the fabric of space-time. Imagine the surface of a small wrinkled balloon. As you begin to inflate it, the wrinkles and creases are pulled taut, they stretch out, and they disappear. As the balloon grows to the size of a planet, any small section of its surface will appear almost perfectly flat to a tiny observer standing upon it. This is how inflation solves the flatness problem. The violent stretching of space drove any initial curvature, no matter how extreme, toward absolute flatness. Our universe is not balanced on a pencil tip by chance. It was flattened into this state by the most powerful expansionary force that has ever existed. The pencil wasn't just balanced, it was forged into a vast, flat, unbendable plane. And what of the uniform temperature, the two villages that shared a culture without ever meeting inflation, solves this riddle with equal grace. Before the Great Expansion began, the entire region that would one day become our observable universe was a tiny subatomic patch. In this infinitesimal space, everything was in intimate contact. Energy and heat were evenly distributed, bringing the whole region to a uniform temperature, a state of thermal equilibrium. All the villages were once a single cozy hamlet. Then inflation happened. It took this tiny uniform connected region and stretched it to colossal astronomical proportions. It flung different parts of this hamlet to opposite ends of the newly formed cosmos, faster than light could ever travel. They lost all contact, separated by the very expansion of space itself. But they carried with them the memory of their shared origin. They retained the same temperature, the same properties imprinted upon them in that first moment before the great separation. The cosmic microwave background is not a coincidence. It is a family portrait, a testament to a time when everything we can see was once together. But inflation was more than just a cosmic steamroller, flattening curves and spreading warmth. It was also the grand architect, the sculptor of the universe. It sowed the seeds of all future structure, and it did so using the strange and ephemeral rules of the quantum world. In the quantum realm, there is no such thing as true emptiness. The vacuum of space, even in this primordial state, is not a void. It is a fizzing, bubbling soup of quantum fluctuations. Tiny, ghostly particles of energy and anti-energy spontaneously pop into existence and annihilate one another in a constant, effervescent dance. These are the jitters of reality itself, a fundamental uncertainty woven into the fabric of space-time. Normally, these fluctuations are microscopic and fleeting, confined to the subatomic world. But during inflation, as space itself was stretched at an unbelievable rate, these tiny quantum ripples were caught in the cosmic tide. They were stretched along with space itself. Microscopic flickers were magnified into vast, continent-sized waves. Tiny, fleeting variations in energy density were frozen into the expanding fabric of the universe. This is the miracle of inflation. It took the inherent uncertainty of the quantum world and made it manifest on a cosmic scale. When inflation finally ended, these magnified fluctuations remained. They were the primordial seeds of structure. The regions that by pure quantum chance were stretched to be infinitesimally denser than their surroundings became gravitational wells. They were the points of cosmic attraction. And the regions that were infinitesimally less dense became the origins of the great voids, the empty spaces between galaxies. The great breath finally subsides. After that frantic, explosive moment of growth, the inflaton field exhausts its energy. It decays, much like a radioactive particle, and in its final act, it releases its immense stored energy back into the universe. This event is called reheating. It floods the cosmos with a hot, dense plasma of elementary particles, quarks, electrons, photons, neutrinos, the very ingredients of the standard hot Big Bang theory. The stage is now set. The universe is vast, it is flat, and it is almost perfectly uniform. But critically, it is not perfectly uniform. It is seeded with the faint quantum whispers of structure, the ghostly blueprints for everything that is to come. The grand overarching architecture of the cosmos, the web of galaxy, clusters the filaments of dark matter. The great walls and the silent voids all owe their existence to those tiny quantum jitters magnified by the universe's first breath. We are the descendants of a quantum fluctuation. Every star in the sky, every planet in orbit, is a testament to the beautiful and creative marriage of the infinitesimally small and the infinitely large. The universe is now a seething opaque fog of pure energy and nascent matter. The light from this era is trapped, bouncing endlessly between charged particles like sunlight in a dense cloud, unable to travel freely. The incredible generative violence of inflation has given way to a glowing, uniform haze. The great beginning has concluded its first act, and a long, quiet darkness is about to descend across the cosmos. The canvas is prepared, but the first strokes of light, the first true stars, have yet to be painted. And the universe would have to wait in a patient and silent twilight for the dawn of that first illumination. And just before we begin our journey into the heart of the great beginning, let us first listen, not with our ears, but with a deeper sense of attention. Let us listen to the silence. Imagine yourself floating in the deep velvet blackness between the stars. It is a quiet, unlike any on Earth. There is no wind rustling through leaves, no distant hum of traffic, no gentle sound of your own breathing in the vacuum. It is a profound, absolute stillness. For centuries, this is what we believed space to be. But as we have learned, space is not silent. It is filled with the faint, residual echo of its own creation, a gentle hum that we call the cosmic microwave background. This ancient light, released when the universe was just 380,000 years old, tells a story of a cosmos that was once a blazing, opaque fog. And as this light was freed, as the fog cleared, the universe entered a new and profoundly different age. It became transparent, yes, but it also became dark. Utterly, completely dark. This was the beginning of the cosmic dark ages. It is an era whose name feels perfectly chosen. For after the brilliant flash of the Big Bang and the lingering glow of its afterheat, the universe plunged into an epoch of profound blackness that would last for hundreds of millions of years. It's a length of time that our minds can barely grasp. Imagine for a moment the entire history of life on Earth, from the first simple cells to the great dinosaurs, from the rise of mammals to the whole story of humanity. All of it is but a fleeting moment compared to the duration of this long, quiet night. The universe was not empty. It was filled with a vast, thin mist of atoms, mostly hydrogen, with a gentle scattering of helium. These were the first complete atoms formed when the universe cooled enough for electrons to finally be captured by protons. The cosmic fog had lifted because light could now travel freely through this neutral gas without constantly bumping into freewheeling electrons. The universe was transparent, yet there was nothing to see. There were no stars to shine, no galaxies to swirl in luminous spirals, no planets to catch the light. There was only the gas, the darkness, and the patient, silent force of gravity. Think of it as a great cosmic winter. The initial heat of creation had faded, leaving behind a deep and pervasive chill. The universe was expanding, and as it expanded, it cooled. The light of the cosmic microwave background stretched and reddened, fading from a brilliant white-hot glow into the invisible microwaves we detect today. All that was left was a canvas of perfect black, dotted with atoms spread almost but not quite perfectly evenly. It is in that tiny imperfection, that not quite, where the entire future of the cosmos was waiting to be written. The echo of creation we see in the cosmic microwave background shows us these minuscule variations regions where the gas was just a fraction of a percent denser than the regions around it. These were not mountains or valleys. They were more like the gentlest ripples on the surface of a perfectly still ocean. In the profound darkness and silence of this cosmic night, these ripples were everything. They were the seeds of all that was to come. And they were the places where gravity, the universe's most patient sculptor, would begin its slow and monumental work. Gravity is a force that is both relentless and incredibly weak. It works on everything, but its touch is so light that it needs immense amounts of mass and immense amounts of time to make its presence felt. In the early universe, it had both. The darkness was its workshop, and 100 million years was its afternoon. Slowly, almost imperceptibly, gravity began its song. It was a whisper, not a command. In those slightly denser regions of gas, there were infinitesimally more atoms. This meant there was an infinitesimally stronger gravitational pull. More atoms were gently drawn toward this center of gravity, making it even denser. And as it grew denser, its pull grew stronger still, drawing in more and more material from its surroundings. It is a process of beautiful recursive simplicity. The rich get richer, but the hydrogen and helium atoms were not alone in this dance. The universe we now know is filled with a mysterious invisible substance we call dark matter. It does not shine, it does not reflect light, and it does not interact with ordinary matter in any way except through gravity. During the cosmic dark ages, this dark matter played the leading role. Being much heavier than the ordinary atomic matter and immune to the outward push of radiation, it began to clump together first. It formed vast, invisible halos, great spherical clouds of gravitational influence. These dark matter halos became the scaffolding of the cosmos, the invisible skeletons around which everything else would form. The ordinary gas, the hydrogen, and helium felt the gravitational pull of these halos and began to fall into them like streams of water flowing into a deep well. Imagine countless invisible gravitational basins forming in the dark. And into these basins, the primordial gas of the universe began to pool. For millions upon millions of years, this was the only action in the cosmos, the slow, silent gathering of matter. The universe was holding its breath, concentrating its substance in countless pockets scattered across the expanding void. Inside one such pocket, a cloud of hydrogen and helium gas was growing ever denser. As the atoms fell inward, they began to bump into each other, converting their falling energy into heat. The cloud began to warm. But for a star to be born, the cloud must not just get denser. It must get dense enough to collapse under its own weight. It needs to cool down to release that heat so that gravity can continue its work of compression. Here, the first clouds faced a unique challenge. Stars today are formed in clouds rich with heavier elements like carbon and oxygen. These elements are excellent radiators. They are very efficient at shedding heat and allowing the cloud to cool and collapse. But these first clouds contained no such elements. They were made of pure primordial gas forged in the Big Bang. Hydrogen and helium are not very good at cooling things down. This meant that the first collapsing clouds of gas had to be enormous, hundreds of thousands of times the mass of our Sun, just to have enough gravity to overcome their internal heat and pressure. And so, inside one of these colossal, slowly collapsing clouds, a core began to form. A dense, hot knot of hydrogen gas squeezed by the unimaginable weight of the material above it. The pressure was building. The temperature was soaring. Millions of years of slow gravitational squeezing were now culminating in a final frantic rush. The core became a protostar, a star in waiting. Atoms were crushed together so tightly that their structures began to break down. The temperature climbed past thousands, then tens of thousands, then millions of degrees. And then it happened. In the heart of that dense, seething core, the pressure and temperature reached a critical point, a point where the fundamental forces of nature gave way. Two hydrogen nuclei, two simple protons that had been repelling each other for their entire existence, were slammed together with such unimaginable force that they fused. In that single, tiny, monumental instant, a new element was born, helium, and a flicker of energy was released. Nuclear fusion had begun. A star was born. For the first time in over 200 million years, there was light. In the absolute unending blackness of the cosmic ocean, a single lighthouse had just been lit. It wasn't a gentle glow. This was a population 3 star, as astronomers call them, the very first generation. Forged from pure primordial fuel and unburdened by heavier elements, it was a celestial titan, a monster of a star. It was perhaps 300 times more massive than our own Sun, and 1,000,000 times more luminous. It did not shine with the warm yellow light of our familiar star. It blazed with a fierce, brilliant blue-white intensity, so hot that most of its light was radiated in the high-energy ultraviolet part of the spectrum. Imagine that moment. For an eternity, there had been only darkness. The universe knew only the fading, invisible glow of its own birth. And now, a point of searing light. It had no planets to illuminate, no neighboring stars to greet. It was utterly magnificent alone, a solitary jewel burning in an infinite void. Its light began to race outwards, a spherical shockwave of pure energy traveling through the neutral hydrogen gas that surrounded it. This light was not just for seeing. It was a force of transformation. The high-energy ultraviolet photons streaming from this new star were powerful enough to do something the universe hadn't seen since its earliest, hottest moments. They began to strip the electrons from the surrounding hydrogen atoms. An atom that has lost its electron is called an ion. This process, happening on a cosmic scale, is called reionization. The first star began to carve a bubble of ionized gas around itself in the vast sea of neutral darkness. Inside this bubble, the universe was once again a plasma, a hot soup of free protons and electrons, just as it had been in the very beginning. From a distance, it would have looked like a single growing sphere of transparency clearing out a cosmic fog. This first star was not alone for long. The same patient work of gravity that had formed it was happening in countless other dark matter halos across the universe. One by one, then in dozens, then in thousands, other lighthouses began to switch on. Each one was a massive, brilliant blue-white giant. Each one began to inflate its own bubble of ionized plasma. The long dark night of the universe was finally coming to an end. It was not a sudden sunrise, but a slow creeping dawn. The bubbles of light and ionized gas grew, and as more and more stars were born, these bubbles began to overlap, merging into larger and more complex structures. The darkness was in retreat. The cosmic winter was giving way to the first spring. The light was returning, but the lives of these magnificent first stars were as brief as they were brilliant. Because they were so massive, they burned through their nuclear fuel at a furious, unsustainable rate. Our sun will live for 10 billion years. These first stars lived for only a few million. Their end was as spectacular as their birth. They died in unimaginably powerful explosions, supernovae, that blasted their contents out into the surrounding space. And in those final violent moments, they performed one last crucial act of creation. In the crushing pressures of their explosive deaths, they forged the first heavy elements the universe had ever seen. Carbon, oxygen, silicon, iron. All the elements that are essential for rocky planets, for complex chemistry, and for life itself were born in the hearts of these dying first stars. They seeded the cosmos with new possibilities. The pristine clouds of hydrogen and helium were now sprinkled with this precious stellar dust. The next generation of stars would form from this enriched material. They would be smaller, they would live longer, and they would be capable of creating even heavier elements. The universe was learning, evolving, becoming more complex. The first dawn was more than just the end of the darkness. It was the moment the universe began to build its own future. The gravity from these first stars and the dark matter halos they lived in continued to pull in more and more gas. Their explosive deaths sent out shock waves that compressed nearby gas clouds, triggering new waves of star formation. These weren't just lonely stars anymore. They were the seeds of the first galaxies. They were the anchor points, the luminous nodes around which matter would continue to gather, pulling on the long, invisible filaments of gas and dark matter that stretched between them. The solitary points of light were beginning to connect to trace the outlines of a far grander and far more intricate structure. The universe was no longer just lighting candles in the dark. It was beginning to weave the luminous tapestry we now call the cosmic web. For centuries, this is what we believed space was: an eternal, silent, and unchanging emptiness, a static backdrop for the transient lights of stars and planets. But we were listening for the wrong kind of sound and looking for the wrong kind of motion. In the deep quiet of the early universe, a force was at work, a force as silent as the vacuum itself, yet more powerful than any explosion. It was the patient, persistent, and cumulative whisper of gravity. After the initial flash of creation, the universe was a remarkably uniform place, a vast, expanding mist of hydrogen and helium, almost perfectly smooth, almost perfectly the same in every direction. But almost is the most important word in the entire history of the cosmos. Scattered throughout this primordial fog were regions infinitesimally denser than their surroundings, tiny accidental gatherings of matter, no more significant than a single extra grain of sand in a desert. In the grand silence, gravity noticed these imperfections. It does not shout, it merely pulls a gentle, inexorable tug. And it has all the time in the world. Where there was slightly more matter, there was slightly more gravity. This faint gravitational pull began to draw in more matter from the surrounding regions, hollowing out the space around it. As the clump grew, its gravitational influence grew, with it allowing it to pull in even more material, even faster. It's a principle of accumulation, the universe's own story of the rich getting richer. A cosmic whisper that over millions of years would grow into a symphony of creation. This was the beginning of the great weaving, the first threads being pulled in the celestial loom. These tiny, overdense seeds were the anchor points upon which the entire tapestry of the cosmos would be spun. The silent architect had begun its work, sketching the blueprints for a structure of unimaginable scale, using nothing but the quiet insistence of attraction. Imagine looking out into this young cosmos. You would not see galaxies yet. Instead, you would see ghostly shimmering clouds of gas, hundreds of times smaller than our own Milky Way, slowly collapsing under their own weight. These were the proto-galaxies, the first humble hamlets of the universe. Inside them, the first stars ignited, massive, brilliant, and short-lived. They were the first sparks of light in the overwhelming dark. These were the building blocks, the fundamental units from which everything larger would be made. The universe, it turns out, builds from the bottom up. It is a story of hierarchy, of small things coming together to form greater wholes. This process is not gentle, nor is it neat. It is a slow, cosmic dance of gravity and momentum. Picture two of these small primordial galaxies, each a swirling collection of a few million stars and vast clouds of gas. Pulled by their mutual gravity, they begin to approach one another. Over millions of years, the gap closes. They do not collide like two solid objects, but rather they pass through each other, their stars sliding past one another like ghosts. But their gravity is no ghost. It latches on, warping and stretching each galaxy. Great sweeping arms of stars and gas are flung out into space, creating what astronomers call tidal tails, luminous, graceful arcs that trace the history of the encounter. After their first pass, gravity pulls them back again, their dance becoming tighter, more intimate. They merge their stars and gas clouds, mingling, churning, until a single, larger, and more chaotic galaxy is formed. The collision of gas clouds triggers a firestorm of new star formation, a brilliant burst of blue and white light that announces the birth of a new, more complex entity. This is how galaxies grow. It is a process of cannibalism and consolidation, a celestial history of mergers and acquisitions written in the language of starlight and gravity. Our own Milky Way is a testament to this history. It is not a single pristine creation, but a composite and amalgamation of countless smaller dwarf galaxies, consumed over billions of years. Within our galaxy's halo, astronomers can still see the faint trails of these ancient meals, streams of stars that move together, the last remnants of a small galaxy, long since torn apart and digested by our own. We live inside a structure built from the ruins of others, a city of stars whose foundations are the remnants of forgotten celestial villages. This process continues even today. The Milky Way is currently in the slow process of consuming the Sagittarius dwarf galaxy and others besides. We are still growing, still participating in this ancient, hierarchical construction. It is a reminder that the universe is not a finished object to be observed, but an ongoing process in which we are deeply embedded. The weaving did not stop. It is happening all around us on timescales that dwarf our human lives. As we pull our perspective back away from the intimate dance of individual galaxies, a new and even more breathtaking pattern begins to emerge. The galaxies are not scattered randomly through space like dust motes in a sunbeam. They are organized. They are arranged in a vast interconnected structure of astonishing beauty and complexity. This is the cosmic web. Imagine a network stretching across billions of light years. It is made of immense luminous filaments, like the glowing threads of a spider's web. These filaments are the great highways of the universe, rivers of galaxies flowing through the dark. They are composed of thousands, even hundreds of thousands of galaxies, all bound together by their shared gravity. Where these filaments intersect, you find the great cosmic cities, the galaxy clusters. These are the most massive gravitationally bound objects in the universe. Dense, brilliant hubs containing thousands of galaxies, all orbiting a common center, swimming in a sea of superheated gas. Our own galaxy, the Milky Way, resides in a quieter suburban outskirt of one such filament, a part of the Laniakea supercluster, a name which in Hawaiian means immeasurable heaven. And between these glowing filaments and brilliant clusters lie the voids. These are the great cosmic deserts, the silent oceans of the universe. They are immense, almost unfathomably empty regions stretching for hundreds of millions of light years across. Here galaxies are rare and the universe is darker, colder, and quieter than anywhere else. To journey through a void would be a profound experience of solitude. For eons, you would travel through a near-perfect emptiness, the bright filaments of the cosmic web receding into the distance until they were just a faint, hazy glow on the horizon of your perception. The existence of these voids is just as important as the existence of the filaments. They are the negative space that gives the web its shape, the quiet that gives the symphony its structure. They are the result of those primordial regions that were slightly less dense from which matter was pulled away to build the great structures elsewhere. The cosmic web is the largest known structure in the universe. It is the grand tapestry woven by gravity over 13 billion years. It is a physical record of the universe's history, its structure dictated by those minuscule density fluctuations in the moments after the Big Bang. Looking at a map of the cosmic web is like looking at a fossil of creation itself. We see the delicate, intricate, and profound order that has emerged from an almost featureless beginning. It is a structure that is simultaneously robust and delicate, a testament to the patient, persistent power of a single simple force acting on a cosmic scale. And this weaving, this majestic celestial construction, is far from over. As we look out across the cosmos, we can see it happening. We see galaxies in all stages of merging their delicate spiral arms, distorted their cores, ablaze with the light of new stars. We see the great clusters still pulling in matter from the surrounding filaments, growing ever larger, their gravitational dominance shaping their cosmic neighborhood. And we can even see our own future in this process. Our nearest large galactic neighbor, the Andromeda Galaxy, is currently hurtling towards us at a speed of over 250,000 miles per hour. While there is no cause for alarm, the distances are so vast that the collision will not properly begin for another 4.5 billion years. It is a powerful reminder of our place in this dynamic cosmos. When our two galaxies finally meet, it will not be a cataclysmic crash. The space between stars is so immense that direct collisions will be exceptionally rare. Instead, it will be a slow gravitational embrace. Over hundreds of millions of years, the two galaxies will merge, their structures disrupted, their stars and gas clouds reshuffled into a new, larger, and likely elliptical galaxy, a creation that some have already nicknamed Milkomeda. Our descendants, if they exist, will look up at a night sky, transformed, a sky filled with the evidence of this grand creative act. The universe is not static. It is a place of constant creation, transformation, and emergence. From a smooth, simple fog, it has woven itself into a structure of filaments, clusters, and voids, a web of breathtaking intricacy. And at the heart of it all is gravity, the silent architect relentlessly pulling matter together, building stars, galaxies, and the very fabric of the cosmos. Yet, as astronomers began to map this magnificent structure, a profound and deeply unsettling puzzle emerged. When they measured the speeds of galaxies orbiting within clusters, they found them moving far too fast. The gravity generated by all the stars and gas they could see, all the luminous matter in the universe, was simply not enough to hold these clusters together. By all accounts, these great cosmic cities should have flown apart billions of years ago. Likewise, when they observed individual galaxies like our own, they saw that the outer stars were orbiting the galactic center just as quickly as the inner stars, defying the known laws of gravity. It was as if some unseen mass, some immense gravitational anchor, was holding everything in place. The majestic cosmic web, with its glowing filaments and brilliant clusters, seemed to be built upon an invisible foundation. The visible matter, the stuff of stars and planets and ourselves, appeared to be little more than a dusting of light upon a far grander unseen structure. The tapestry we could see was real, but the loom upon which it was woven remained completely hidden from our view. Something else was out there in the dark spaces between the stars and pervading every galaxy. Something that did not shine or reflect light or interact with us in any way except through its silent, overwhelming gravitational pull. The universe, we were beginning to realize, was far stranger and more mysterious than we had ever imagined. The greatest part of its substance was missing. We had mapped the glowing web, but now we had to confront the invisible scaffolding that gives it its form and its very existence. For centuries, this is what we believed space was: an eternal, silent, and unchanging emptiness, a static backdrop for the transient lights of stars and planets. But we were listening for the wrong kind of sound and looking for the wrong kind of motion. In the deep quiet of the early universe, a force was at work, a force as silent as the vacuum itself, yet more powerful than any explosion. It was the patient, persistent, and cumulative whisper of gravity. After the initial flash of creation, gravity was the universe's great sculptor. It began to coax the thinly spread hydrogen and helium atoms into wisps and filaments, pulling them from the slightly less dense regions into the slightly more dense ones. Over millions of years, these filaments were meant to thicken, to knot together, and at their densest intersections to collapse and ignite the first stars. This was the grand, elegant story of cosmic structure, a celestial ballet choreographed by a single, well-understood force. We had the laws of motion, we had the law of universal gravitation, and we had the ingredients. We thought we understood the recipe. We ran the simulations. We did the math. And a picture emerged of how galaxies should form and behave. And for a time, it seemed to match what we saw. But when our instruments grew sensitive enough, when we learned to look not just at the light, But at the motion, we found something profoundly unsettling. We discovered that the performance we were watching was being directed by an invisible puppeteer. The celestial ballet had a ghost in its machine, a silent partner whose influence was everywhere, yet whose presence was a complete and utter mystery. The first hint of this enigma came not from the farthest reaches of the cosmos, but from our own cosmic neighborhood. In the 1970s, an astronomer named Vera Rubin was doing something that seemed at first rather routine. She was meticulously measuring the speed of stars at different distances from the center of nearby galaxies, like our own cosmic cousin Andromeda. The expectation was simple, based on everything we knew from Newton and Kepler. Just as planets farther from our Sun move more slowly, distant Neptune crawling along compared to swift Mercury, so too should stars at the edge of a galaxy's disk move much more slowly than those near its bright, dense center, where most of the visible mass resides. The gravitational pull should weaken with distance, and the stellar orbits should slow down accordingly. But that is not what Vera Rubin found. Again and again, with painstaking precision, her data told an impossible story. The stars at the very edge of the galactic disk, far from the luminous core, were moving just as fast as the stars much closer in. In fact, their speeds were staggeringly high. They were moving so fast that the gravity from all the visible stars, gas and dust in the galaxy shouldn't have been nearly enough to hold them in their orbits. By all rights, these outlying stars should have been flung off into the intergalactic void like children letting go of a carousel spinning far too quickly. Yet there they were, perfectly stable, tracing their calm celestial arcs. The only way this could be possible was if there was a colossal amount of unseen mass, a vast invisible halo of something surrounding the entire galaxy. This halo had to extend far beyond the visible light of the stars, and its gravitational grip had to be what was holding those speeding stars in place. It was a phantom presence inferred only by its gravitational effects. The matter we could see, the brilliant stars, the glowing nebulae, the dust lanes, was apparently just the tip of the iceberg. The data suggested that for every gram of visible matter, there were 5 or 6 grams of this mysterious, unseen substance. We gave it a simple, haunting name: dark matter. This was not a small correction to our models. This was a revolution. It was as if we had spent our entire history mapping a great forest by observing only its flowers, and had suddenly realized that the vast, unseen root system beneath the soil was where the real mass and structure lay. The universe we saw was not the universe that was. And so, we began to look for this invisible scaffolding elsewhere. If it was holding together individual galaxies, its presence should be felt on even grander scales. Astronomers turned their attention to the great cosmic cities' galaxy clusters. These are immense congregations of hundreds or even thousands of galaxies, all bound together by their mutual gravity into a single colossal entity. Here too, the same strange story repeated itself, but written in even larger letters. When we measured the motions of individual galaxies within these clusters, we found them buzzing around like angry bees in a hive, moving at tremendous velocities. Once again, their speed was far too great. The combined gravity of all the visible matter in all the galaxies of the cluster wasn't nearly enough to keep them from flying apart. The entire cluster should have dissolved into the void millions of years ago. For it to remain a coherent structure, there had to be an immense reservoir of extra mass, a gravitational glue holding it all together. The calculations were undeniable. The clusters were filled with dark matter, vast clouds of it, permeating the spaces between the galaxies, its invisible weight dominating the entire system. Still, seeing the effects of something's gravity is one thing. To truly believe in its existence, we long to see its presence more directly. But how do you see something that by definition does not interact with light? It neither shines nor reflects nor casts a shadow. The answer came from one of Einstein's most beautiful predictions. He taught us that mass warps the fabric of space-time itself. A massive object creates a kind of dimple in the universe, and light, as it travels across this fabric, must follow the curves. This phenomenon is called gravitational lensing. Imagine a heavy ball placed on a stretched rubber sheet. It creates a dip. If you roll a small marble past the ball, its path will be deflected by that dip. Light behaves in much the same way. When we look at a very distant galaxy, the light from it has traveled for billions of years to reach us. If between us and that distant galaxy there sits a massive cluster of galaxies, the cluster's immense gravity will warp space-time. The light from the background galaxy will be bent, distorted, and magnified as it passes through this cosmic lens. We can see this effect clearly. Distant galaxies behind massive clusters often appear smeared into strange arcs, or their images are duplicated, creating a celestial hall of mirrors. And here was the ultimate test. We could calculate how much lensing should occur based on the mass of the visible galaxies in the cluster, and we could measure how much lensing was actually happening. The two numbers did not match. The light was being bent far more dramatically than the visible matter could account for. The lensing revealed the true shape of the gravitational field, and it showed a vast, smooth halo of mass that was much, much larger than the clumpy collection of visible galaxies within it. We were for the first time seeing a direct map of the dark matter's presence. It was like seeing the silhouette of an invisible person because of the way the rain curved around their body. The invisible architect had left its footprint in the very fabric of reality, and we had finally learned how to see it. With this evidence from spinning galaxies, from buzzing clusters, and from warped light, the picture of our universe fundamentally changed. Dark matter was not a niche problem or a minor anomaly. It was the primary ingredient. This substance, which we cannot see or touch, which passes through our bodies and our planet as if they were ghosts, makes up about 85% of all the matter in the cosmos. The atoms that form our world, the stars, the planets, the air we breathe, all of it, is just a 5/6 dilution, a sprinkle of cosmic dust on a vast invisible framework. This realization sent us back to the very beginning, to those first filaments of gas after the Big Bang. Our old models with only ordinary matter had struggled. Gravity acting on such a small amount of material would have been too gentle a force. The initial expansion of the universe was so powerful that it would have likely smoothed out any small density fluctuations before they had time to grow and collapse into galaxies. The universe would have remained a thin, uniform, and ultimately lifeless soup. But with dark matter, the story works. Because dark matter does not interact with light or radiation, it was not pushed around by the intense energy of the early universe. While ordinary matter was being buffeted and smoothed out by photons, the dark matter was free to respond to gravity's call alone. It began to clump together much earlier and much more effectively. It formed the first gravitational wells, the deep pits in space-time. It built the invisible scaffolding, the vast interconnected network of filaments and halos that we now call the cosmic web. And then, like water flowing into a pre-dug riverbed, the ordinary matter was pulled into these dark matter structures. It settled in the hearts of the dark matter halos, where it could finally cool, condense, and collapse. The dark matter built the cathedrals, and the ordinary matter became the stained glass windows illuminated from within by the nuclear fire of the first stars. Every galaxy we see, including our own Milky Way, sits within a vast, stabilizing halo of this enigmatic substance. It is the silent architect of our cosmic home, the foundation upon which everything we know is built. And so the great hunt began. What is it? We know what it is not. It is not dark clouds of normal matter, because they would absorb or emit radiation in other wavelengths. It is not a sea of black holes or dead stars, as we would detect them through gravitational lensing on smaller scales. It must be something entirely new, a particle not included in our standard model of particle physics. Scientists have proposed many candidates, the most popular being a class of particles called WIMPs, or weakly interacting massive particles. These are hypothetical particles that are heavy, and as their name suggests, they interact with other matter only through gravity and the weak nuclear force, making them almost impossible to detect. All over the world, we are now listening for the faintest whisper of this invisible world. Deep underground in old mine shafts and mountain laboratories, shielded by kilometers of solid rock from the confusing noise of cosmic rays, scientists have built detectors of extraordinary sensitivity. They are vats of supercooled liquid xenon, or arrays of pristine crystals waiting in the absolute dark and quiet for the vanishingly rare event of a single dark matter particle bumping into a single atomic nucleus. A tiny flash of light, a minuscule vibration that is the signal they are searching for. It is perhaps the most difficult and profound search in modern science, a quest to finally meet the ghost in the machine, to shake hands with the architect who built our world. For decades, we believed this was the grand inventory of the cosmos. We had the small fraction of ordinary matter, the stuff of stars and ourselves, and we had the much larger portion of dark matter, the invisible gravitational scaffolding. Together, their gravity governed the universe. The great cosmological question became a simple cosmic competition, was the relentless outward push of the Big Bang's expansion stronger than the collective inward pull of all this matter's gravity. For a long time, the debate centered on the universe's ultimate fate. Would it expand forever, growing ever colder and emptier? Or was there enough matter, visible and dark, combined to eventually halt the expansion and pull everything back together in a fiery Big Crunch, a reverse of the Big Bang? To settle the question, we just needed to measure how quickly the expansion was slowing down. We pointed our most powerful telescopes at the most distant reliable mile markers. We could find a special kind of exploding star to chart the history of cosmic expansion. We were confident in what we would find. The only question was how much the universe was breaking. But the universe, as it so often does, had one more secret, one more layer of mystery, more profound than we could have ever imagined. When the data came back, it was not just surprising. It was impossible. The expansion of the universe was not slowing down at all. It was speeding up. Something was actively pushing the universe apart, a force working against gravity on the largest of scales, a form of repulsive energy inherent to the fabric of space itself. The silent architect had a rival, an even more mysterious force, working not to build, but to expand. For millennia, we lived under a simple and powerful assumption, an idea born from watching an apple fall from a tree and a planet trace its arc across the sky. The assumption was that the universe on the grandest of scales was governed by a single, majestic force, gravity. After the initial violent push of the Big Bang, we believed the cosmos was like a ball thrown high into the air. Gravity, the great collector, the patient shepherd of matter, was pulling on it relentlessly. The only real question, the grandest question in cosmology for much of the 20th century, was whether gravity was strong enough. Would it eventually slow the ball to a stop and pull it back down into a fiery, big crunch, a cosmic echo of the Big Bang in reverse? Or would the ball have just enough momentum to escape its expansion, slowing forever, coasting into an eternity of cold, quiet emptiness? The debate was fierce, the stakes cosmic. Either way, the story had a clear antagonist. A clear force of cosmic destiny, gravity, was breaking the universe. And so, with new technologies and telescopes of unprecedented power, two teams of astronomers set out in the 1990s to settle the question once and for all. They were not looking for a new mystery. They were simply trying to measure the rate of the slowdown. They were trying to weigh the universe to read its final chapter. To do this, they needed a measuring stick of truly cosmic proportions. They needed what astronomers call a standard candle. The principle is elegantly simple. If you have a line of identical candles stretching down a long, dark hallway, you can tell how far away each one is just by how bright it appears. The dimmer the candle, the farther away it must be. To measure the cosmos, you just need to find a candle bright enough to be seen across billions of light years, and one whose true intrinsic brightness is always the same. Nature, in its violent and beautiful way, provided one. It is called a type Ia supernova. Imagine a white dwarf star, the dense, smoldering core left behind by a star like our Sun. It is a cosmic ember slowly cooling over eons. But if this white dwarf is not alone, if it has a companion star locked in a gravitational dance, it can be reborn in fire. It begins to siphon gas from its neighbor, pulling a stream of hydrogen and helium onto its surface. For millions of years it grows heavier, more compressed, its core heating up. It continues this stellar theft until it reaches a precise, unchangeable limit of mass, a tipping point known to physics as the Chandrasekhar limit, about 1.4 times the mass of our Sun. At that exact moment, the pressure and temperature in its core become so immense that a runaway thermonuclear reaction ignites. In a flash, the entire star detonates. It is not just an explosion. It is a meticulously calibrated cosmic event. Because every type Ia supernova is triggered at the exact same mass, the resulting explosion has the exact same predictable, astonishing brightness. For a few weeks, a single exploding star can outshine its entire host galaxy. Here, then, was the perfect standard candle, a beacon bright enough to be seen from the far side of the observable universe. The plan was clear. The astronomers would hunt for these distant explosions. By measuring their apparent dimness, they could calculate their distance with great precision. At the same time, they could measure the supernova's redshift, the stretching of its light waves caused by the expansion of space. This would tell them how fast its home galaxy was moving away from us. By comparing the distance to the speed for supernovae at many different distances, and therefore from many different eras of cosmic history, they could build a history of the universe's expansion. They could finally measure how much the universe was slowing down. They were charting the flight of the ball that was thrown at the beginning of time. They pointed their telescopes to the deepest, darkest patches of the night sky, and they waited. They found their supernovae, faint, ancient ghosts of light that had traveled for 5, 6, 7 billion years to reach us. They were snapshots of a younger, middle-aged universe. And when the data came in, it made no sense. It was wrong. It had to be wrong. Again and again, the calculations were checked, the assumptions questioned, the equipment recalibrated, but the numbers would not yield. The distant supernovae, the ancient ones, were dimmer than they had any right to be. Consistently, stubbornly dimmer. There is only one way a standard candle of known brightness can appear dimmer than expected. It must be farther away than you thought. And if these galaxies, from billions of years ago, were farther away than the prevailing models predicted, it could only mean one thing. The journey of their light to us took longer than expected because sometime in the intervening eons, the space it was traveling through had stretched more than it was supposed to. The expansion of the universe had not been slowing down. It had been speeding up. This was impossible. It was absurd. It was like throwing a ball into the air and watching it fall for a second, only to see it suddenly reverse course and rocket away from you into the sky with ever-increasing speed. It was like a car that was supposed to be coasting to a stop had suddenly silently floored its accelerator. Gravity, the undisputed master of the cosmos, was losing a war it was supposed to win. Something else, some other force was at work, a force that did not pull, but pushed. A force that was not fading with time, but growing stronger. The discovery was so profound, so contrary to all expectation, that the two teams of scientists were almost afraid to announce it. But their data collected independently told the same impossible story. In 1998, the world was told that the universe was not just expanding, but that its expansion was accelerating. The force driving this acceleration was given a name as mysterious as its nature, dark energy. It is a name that invites misunderstanding. It is not dark in the sense of being sinister, nor is it related to dark matter, the unseen mass that holds galaxies together. It is dark in the sense of being utterly unknown. We do not know what it is. We only know what it does. It acts as a kind of anti-gravity, a repulsive force inherent in the fabric of space-time itself. And unlike gravity, which is generated by matter and energy, and thus gets weaker as the universe expands and things spread out, dark energy seems to be a property of the vacuum. As the universe expands, it creates more space, more vacuum, and in doing so, it creates more of this repulsive energy. The more space there is, the more push there is. It is a runaway effect, a cosmic feedback loop. Suddenly, the history of the universe was recast as a grand cosmic tug-of-war. For the first several billion years after the Big Bang, the universe was smaller, denser. Matter and dark matter were packed closely together. In this era, the attractive force of gravity was dominant. It was indeed slowing the expansion down, just as everyone had expected. It was forming the great cosmic web of galaxies and clusters, pulling the universe into the magnificent structures we see today. But all the while, as space expanded, the density of matter slowly decreased and gravity's grip weakened. At the same time, the total amount of dark energy was growing with the growing volume of the cosmos. About 5 billion years ago, a quiet but momentous tipping point was reached. The relentless, repulsive push of dark energy finally became equal to the attractive pull of gravity, and then it surpassed it. At that moment, the universe stopped breaking and gently, imperceptibly at first, began to accelerate. The cosmic car, which had been coasting up the hill, crested the peak and began to roll down the other side, picking up speed. It is an acceleration that continues to this day, and one that appears to be shaping the ultimate destiny of everything. The implications of this discovery are staggering, stretching the imagination to its breaking point and painting a picture of the far future that is both majestic and profoundly lonely. If dark energy remains constant or continues to grow, the fate of our universe is not a fiery big crunch, but a big freeze, or the heat death. The acceleration will continue forever. Galaxies not gravitationally bound to our own local group will be pushed away from us faster and faster. Think of what this means for a future observer standing on a planet billions of years from now. They will look up at the night sky and see the familiar stars of their own galaxy, the Milky Way perhaps, merged by then with Andromeda into a single vast island of light. But beyond it, there will be nothing. The other galaxies, the trillions of island universes that fill our skies today, will have been pushed away with such velocity that their speed relative to us will exceed the speed of light. Not that they are traveling through space faster than light. Nothing can, but that the space between us and them will be stretching faster than light can cross it. They will have crossed a cosmic event horizon, their light no longer able to reach us ever again. They will have vanished from our sky as if they had never been. Our universe of countless galaxies will shrink from our perspective to a single isolated island of stars in an infinite, uncrossable, and perfectly black ocean of emptiness. The story does not end there. Over truly unimaginable timescales, the stars within this final galaxy will themselves burn out. The great stellar furnaces will exhaust their fuel, becoming cold, dark remnants, white dwarfs, neutron stars, black holes. The universe will grow ever colder, ever darker, ever emptier. Even the black holes, the final bastions of gravity, are thought to slowly evaporate over googles of years through a process called Hawking radiation, returning their energy to the void as a faint, cold whisper of particles. Eventually, the universe will approach a state of maximum entropy. It will become a vast, near infinitely large, and unimaginably cold soup of stray photons, neutrinos, and other fundamental particles drifting aimlessly through a dark and silent expanse. All structure will be gone. All temperature differences will have evened out. There will be no flow of energy, no process, no change. Time itself will lose its meaning, for there will be no events to mark its passing. This is the heat death, a final, perfect, and eternal equilibrium of cold and darkness. It is not a violent end, but a gradual fading into utter stillness, the long, slow, silent sigh of a universe that has finally run its course. This is the future that the discovery of dark energy has laid before us, a future of ultimate isolation and eternal quiet. Our journey to understand the universe's great beginning has led us to an unsettling prophecy of its ultimate end. We began with a flash of infinite heat and light, and it seems we are destined for an eternity of absolute cold and darkness. But in science, every answer gives rise to a dozen new, more profound questions. The discovery of this dark, accelerating force was not just a conclusion about our fate, but a profound new puzzle about the very nature of our reality. What is this energy of the void? Is it truly a constant, or does it change over time? Is its existence just a random feature of our cosmos, or does it hint at a deeper principle, perhaps the existence of other universes with different laws? The darkness that will one day consume the sky has for now illuminated the vastness of our own ignorance. Our story of a singular great beginning has been thrown into question. For this universe, this set of laws, this delicate balance between gravity and the void that allows for our existence now seems more mysterious than ever. It forces us to ask, as we stand here between the brilliant flash of the past and the encroaching dark of the future, was this the beginning of everything, or just the beginning of our story? For millennia, we lived under a simple and powerful assumption, an idea born from watching an apple fall from a tree and a planet trace its arc across the sky. The assumption was that the universe on the grandest of scales was governed by a single, majestic force, gravity. After the initial violent push of the Big Bang, we believed the cosmos was like a ball thrown high into the air. Gravity, the great collector, the patient shepherd of matter, was pulling on it relentlessly. The only real question, we thought, was whether its pull was strong enough to eventually halt the expansion and bring everything crashing back together, or if the universe would drift apart forever into a cold and silent darkness. But the universe, as it always does, held a deeper surprise. When we looked out with our most powerful eyes, we found that the expansion was not slowing down at all. It was accelerating. Some hidden energy, woven into the fabric of space-time itself, was pushing everything apart, overwhelming gravity on the largest scales. And with this discovery, our story of the cosmos opened into its final, most profound chapter. If the universe has a hidden energy driving it towards an unknown future, then we must turn and face the most fundamental question of all. Not just how it began, but what it began from. We have traveled back to the very first second, to the threshold of a blinding light. But now we must ask, what lies on the other side of that door? The question itself feels elemental. What happened before the Big Bang? It's a question a child might ask, simple and direct. Yet, it is perhaps the most difficult question in all of science, because it challenges the very language we use to understand the world. The word before implies a moment in time that precedes another, but our entire journey has shown us that the Big Bang was not an explosion in space, but an explosion of space. It was the origin point, not just of matter and energy, but of time itself. To ask what came before the beginning of time is like standing at the North Pole and asking, which way is north? The question dissolves. All directions from the North Pole are south. In the same way, all directions in time from the Big Bang point forward into the future. From our vantage point within this universe, there is no before in the way we experience it. The laws of physics as we know them break down at that singularity, that point of infinite density. Our mathematics returns nonsense. Our stories fall silent. And yet, the human mind is not content to stand at the edge of a mystery and simply turn away. The silence is not an end, but an invitation. If our current understanding of time and space cannot cross that boundary, perhaps it is our understanding that is too small. Perhaps the Big Bang was not the beginning of everything, but only the beginning of our everything. Imagine our universe, all of it. Every star, every galaxy, every cluster stretched across billions of light years is contained within a single room. It is a vast and beautiful room filled with intricate patterns and glowing chandeliers. We have spent our entire existence mapping its corners, studying the light that filters through its windows, and tracing our history back to the moment the door first opened and light poured in. That moment was our Big Bang. For a long time we believed the room was all there was. But now, a new generation of thought of physics and philosophy encourages us to gently push on the walls of this room. It asks us to consider that the door we came through does not open from nowhere, but from a hallway. A vast, misty, perhaps infinite hallway. This idea is called eternal inflation. It suggests that the super-fast expansion we saw in the universe's first fraction of a second is not a one-time event. It is the default state of the cosmos. Imagine a vast cosmic ocean of energy bubbling and churning, expanding at an incredible rate forever. Every so often, in a random pocket of this ocean, the inflationary energy calms down, it decays, and a bubble of stability forms. That bubble, cooling and settling, becomes a universe. Our universe. In this vision, our Big Bang was not the Big Bang. It was just a Big Bang. And out there in that eternally inflating superspace, other bubbles are forming constantly. An infinite number of universes, each one a self-contained room, budding off from the great cosmic hallway. This is the multiverse. If we could somehow peek outside our door, we might see countless other doors lining this infinite corridor, each one leading to a different room. Some rooms might be very similar to our own. Others could be wildly different. The physical laws, the fundamental constants that govern our reality, like the strength of gravity or the charge of an electron, might be different in those other universes. Some might be empty and sterile, expanding too fast for galaxies to form. Others might collapse back in on themselves in a mere moment. And some, a rare and precious few, might have just the right conditions for stars to shine, for planets to form, and for something like life to emerge and wonder about it all. Our familiar cosmos is no longer the entire play, but just one act in a drama of infinite scope. This is one possibility, but there are others. Let us return to our room, our universe, and consider a different kind of story. What if this room is not one of many, but is in fact the only room? But what if its story is not written once, but over and over again? This is the idea of a cyclical universe. In this model, our Big Bang was not a singular origin, but part of an endless rhythm, a cosmic breath of expansion and contraction. The universe we see expanding and accelerating might one day reverse its course. Perhaps the hidden energy driving it apart will change its nature over trillions of years. Gravity might once again become the dominant force, pulling all the galaxies back together, faster and faster, until everything space-time and matter collapses into an infinitesimally small, hot, dense point. A big crunch. But this end would not be the final end. It would be a new beginning. From the crucible of that collapse, a new Big Bang could erupt, birthing a new universe from the ashes of the old one. A great bounce. Over and over for eternity. This vision has a deep, poetic resonance, echoing the cycles we see everywhere in nature, the turning of the seasons, the rhythm of life and death, the rising and setting of the sun. It suggests that our universe is not a single linear story with a beginning and an end, but an epic poem told and retold in infinite variations. We are living in one of its stanzas. The matter that makes up your body, the atoms forged in long-dead stars, might have existed in a previous iteration of the cosmos, and they might exist again in the next. The great beginning is not a static event in the distant past, but a recurring dawn. And there is yet a stranger idea born from the most advanced and perplexing corners of theoretical physics. It comes from string theory, the attempt to find a single elegant theory for all of reality. String theory proposes that the fundamental particles we see are not points, but tiny vibrating strings of energy. And it requires that our universe have more than the 3 dimensions of space we experience. Perhaps 10 or 11 or more. So where are these other dimensions? The theory suggests they are curled up too small for us to see. In this framework, our entire 3-dimensional universe might be a membrane or a brain, floating within a higher dimensional space, which physicists call the bulk. Picture our universe as a single sheet of paper in an infinite dark library. Beside it, floating parallel, but unseen, are other sheets of paper, other brains. In this brain cosmology, the Big Bang could have been caused by the collision of 2 of these brain universes in the higher dimensional bulk. The cataclysmic energy of that collision, that clap of cosmic thunder, would be powerful enough to create all the matter and energy in our universe, setting off the expansion we still witness today. Our origin in this story is the echo of a touch, a connection with another reality just beyond the veil of our perception. We live within the reverberations of an event that happened not just in time, but across dimensions. The multiverse of eternal inflation, the cyclical cosmos, the collision of brains. These are not proven facts. They are whispers from the edge of knowledge, mathematical poems written in the language of physics. They are the stories we tell ourselves when our measurements can take us no further. And yet, they all serve a profound purpose. They dismantle the idea that our existence is central, that our reality is the only one. They open the door to a humility that is as vast as the cosmos itself. And this humility leads us to the final, most personal question. It is a question that brings the entire cosmic story right back into this very moment, into our own consciousness. We have found that the universe is governed by a set of fundamental constants and laws that seem exquisitely tuned for our existence. If the force of gravity were just a tiny bit stronger, the universe would have collapsed back on itself long before stars could form. If it were a tiny bit weaker, galaxies would never have coalesced. If the energy that drives the cosmic expansion were slightly different, the universe would be empty and sterile. Why? Why does the universe appear so perfectly arranged for life to emerge? This is the puzzle of fine-tuning. One answer is what is known as the anthropic principle. It comes in 2 flavors. The first, the weak principle, is a simple statement of logic. Of course, we find ourselves in a universe that can support life, because if the universe were any different, we wouldn't be here to observe it. In the multiverse model with its infinite rooms, it's no longer a surprise. With trillions upon trillions of universes, each with random physical laws, it is inevitable that a few, by pure chance, would have the right combination for life. We are simply living in one of the lucky ones. We are the winners of a cosmic lottery so vast we cannot comprehend the number of tickets. The other flavor, the strong principle, is more philosophical, more provocative. It suggests that perhaps the universe is somehow compelled to have the properties that allow for conscious observers to arise within it. That in some deep, mysterious way, our existence is written into the fabric of the cosmos from the very beginning. That the universe, in a sense, exists to be known. We don't know which, if any, of these ideas is true, but the question itself changes us. It frames our existence not as an accident, but as a deep and meaningful consequence of the cosmos in which we find ourselves. And so our journey ends where it began, with a sense of wonder. We have traveled from the quiet stillness of the night sky back through 13.8 billion years of cosmic history. We have witnessed the birth of galaxies, the forging of stars, and the assembly of the very atoms that now constitute your body. We have walked to the edge of the first second and peered into the quantum fog from which everything arose. And here, at the end of our story, we find that the great beginning may not have been a single event at all. It might be one of an infinite number of beginnings in a vast multiverse. It might be one chapter in an eternal cycle of cosmic death and rebirth. It might be the echo of a collision in a higher dimension. The final answer for now is that there is no final answer. There is only a deeper and more beautiful question. The story of the universe is not a book that is finished and placed on a shelf. It is a story that is still being written. And the most astonishing part is that we who are born of this universe are the ones who are able to read its pages and to write the next lines of inquiry. The same stardust that became the distant nebulae and the silent planets also became your hand. The same fundamental forces that hold galaxies together also hold you together. The same cosmic curiosity that sparked our journey is the same curiosity that flickers within your own mind. You are not separate from this story. You are a living, breathing, thinking part of it. You are the universe's way of knowing itself. Yash. Closing reflection. And so, we bring our journey to a gentle close. We began under a canopy of stars with the simple act of looking up. From that quiet beginning, we traveled through time and space to the very edge of what we know and perhaps what we can ever know. We learned that our home is not a static stage, but a dynamic, evolving creation of unimaginable scale and beauty. We discovered that the great beginning was not a distant sterile event, but the start of a chain of causation that leads directly to this moment, to the quiet rhythm of your own breath. The story of the universe is not out there among the distant galaxies. It is in here. It is the story of us. And to know this, to truly feel this connection, is to understand that even in our smallest moments, we are part of something boundless and magnificent. The great beginning is not over. It is happening now within you.